Hello, I'm Victor Skormin. You and I will work on adaptive control. This is a graduate level course in the controls area. The course will concentrate on methods, models, and applications of the model reference and self-tuning adaptive control theory. We will consider mathematical description, computer simulation, analysis, and design of adaptive control systems. I suggest two textbooks. One is by Landau Adaptive Control, and another one is by Ostrom and Wittenmark Adaptive Control. As I said, I'm Victor Skormin. You see my office room, 2316 Engineering Science. My telephone is here. My email is here. So if necessary, you can always set up an appointment with me using my email. I expect from you to have background in analog and digital state variable control and classical control. I expect from you the ability to work with computer tools like MATLAB and Simulink. Some people prefer vSim, some people will use CC. But you must use computer tools, because without computer tools, a lot of things that we will discuss are meaningless. The topics will include control system design with incomplete information, the model reference approach, local parametric optimization in model reference, application of Lyapunov functions in the model reference, application of positivity and hyperstability principle in model reference control, adaptive identifier and state estimators, adaptive control systems using model reference approach, and then we will concentrate on methods of self-tuning control, which is an alternative adaptive control technique. I will show you recursive least square method procedure as applied to self-tuning systems. We will discuss pole placement design. We will talk about Diophantine equation. We will talk about explicit self-tuning and implicit self-tuning. We will talk about parameter optimization in control systems. I will discuss a little bit of gain scheduling, which is a very straightforward technique used by high-tech companies. And of course, we will be discussing various case studies. I plan to evaluate your success based on test. This test will be given in class. It will be test that covers topics from 1 to 7. It's 30% of grade. You will be required to complete 10 homework assignments. Homework assignments will require you to use computer tools. Homework assignments will be offered on a weekly basis and collected 1 week later. All homework assignments account to 30% of the grade. And then I will give you final exam or project at the end of the semester. And maybe you will do it at home. So also it is assumed that you will follow the regulations imposed on all practicing engineers in American industry. Let me tell you that modern control includes advanced mathematics, special software tools. It includes dedicated microprocessors like flight control computer. It includes advanced hardware, sensors, actuators, and similar devices. Why do we need adaptive control? We need adaptive control because of incomplete information on the controlled process that control system designers and users of control systems facing on a regular basis. You know, it happens because of the oversimplified mathematical description of controlled processes. It happens because of parameter drift in control processes, and it happens because of nonlinearity of control processes. What nonlinearity has to do with incomplete information? The thing is, our control approaches utilize linearization. We normally linearize control system performance within a very narrow range, around the vicinity of the point of operation. The system stays in the vicinity of operational point because of the control system. But if we would change regime of operation, we would change the point of operation, and the point of operation will move along the nonlinear characteristic, and we will be using linearization at a different location, and obviously it would be completely different linear characteristic that we will use to approximate the system. Let me talk about the design problem that is typically done by control system practitioners. First of all, we used to claim that it is given transfer function of the controlled plant, that it is given design specifications, and then we have to satisfy these design specifications in terms of settling time, overshoot, steady state error, maybe system bandwidth, maybe disturbance rejection. And we do it by design of a control law. And the controller H of P has to be designed that the overall system, closed loop system, would meet the design specifications. You saw this problem in 361 class, you saw this problem in 462 class, and you're used to this definition of the design problem. But let's face the reality. You may design problem using the techniques presented in 361, techniques presented in 462. You will test your system in the simulation environment, and you will see that your design system fully complies with the design specifications. See, computer simulation is perfect. But then you're supposed to apply the design controller to the real process. And then you would see that design specifications are not met because of the following situations. If transfer function of the control plant is fully consistent with the transfer function of the plant that was suggested at the design stage, the system will work perfectly. But the real system may have different control plant with different parameters. Even the order of the transfer function could be the same, but parameters of the real system could be different from those that were utilized during the system design. And as a result, there will be poor compliance with the specs. System may even become unstable. The second problem is that parameters of the controlled plant defined at the stage of design may change with time. As airplane flying, there is ice buildup on the control surfaces. If it's a chemical process, then properties of the catalyst change with time. The thermoinsulation is getting destroyed, and as a result, at the beginning, when the brand new system is turned on, it complies with the design specs. But as time goes on, the compliance does not hold. For example, you launch a rocket. At the moment of launch, there is a certain amount of fuel on board. But as rocket approaches the target, fuel is spent, and guess what? You have to control a system with a different inertia. Of course, design specs may not be satisfied. The third requirement, of course, the third situation leading to poor compliance with the design specs is when the transfer function is oversimplified. At the stage of design, you have one transfer function. In the real process, there are components of so-called hidden dynamics, high-order terms in the transfer function, and specification with design. The specifications will not be satisfied. And there are two approaches to address this problem. It's a serious problem. The first approach is robust control. Robust control is a highly mathematical approach, but I will present you the simplified version of the robust control. Look, this is the closed-loop system transfer function of a system. Transfer function of the control plant is G of A and S. A are parameters. In the denominator of the closed-loop system, you can see transfer function of the control plant multiplied by the transfer function of the controller. Let me imagine that this product is much, much greater than 1. This means that this 1 could be neglected in comparison with the product of GA times H of S. If it is neglected, the next what we can do, we can perform cancellation. And the overall transfer function now is equal to 1 divided by the transfer function of the controller. Where is control plant? It is not present there. It looks like we can have the required system performance regardless of the properties of the control plant. There is a problem with this. In order to achieve this condition, we have to have a very large quantity associated with the controller. And inevitably, this increases magnitude of the control efforts in the system. And with the increased magnitude of the control efforts, as you understand, the airplane will be burning too much fuel, the electric machine will have tremendously high current, and this is why practitioners are very cautiously considering robust control. But there is another approach which is more suitable for engineering applications. It's adaptive control. There is a control law. The H of P and S represents the transfer function of the controller, where P is a vector of parameters of the control law. These parameters could be time-dependent. These parameters could be adjustable. And if they are adjustable, then the system can maintain its necessary performance even if the transfer function of the control plant will change. You know, the adaptation law is exactly the function that is responsible for adjustment of parameters of the controller. This function could be very complex. You know, this function, the control law, adjustable control law, will include error in the system. It will include the various signals that could be observed in the system. As a matter of fact, in adaptive control, you will be facing a quite unusual situation. Some of the system parameters will be defined using system signals. I guess you never saw it before. Adaptive control. Characteristics of the controller are changed automatically to achieve and maintain the necessary correspondence between the properties of the controlled process and the controller. I just said it. Adaptive control systems perform continuous accumulation of information on the control process and utilize this information for maintaining the required system performance in spite of incomplete original knowledge of the control process. This concept very explicitly you will observe in self-tuning control systems. Adaptive control systems are capable of learning about the control process. They develop or upgrade mathematical model of the process using online data. They actually perform system identification. Again, you will see this property very clearly defined, very explicitly defined in self-tuning systems. Adaptive control performs control problem or provides, facilitates solution of the control problem, state estimation problem, and parameter estimation problem. So I don't want you to assume that adaptive control is only to build a control system. No. You can build control system, you can perform state estimation, and you can perform parameter estimation. Adaptive control includes model reference control, as I said, and self-tuning control. And in addition, in adaptive control, there is a special technique known as gain scheduling. So in my course, we will talk in all details about model reference and self-tuning, and we'll talk about gain scheduling. But the concept of gain scheduling is a little bit different. It is used, but many people do not view it as adaptive control. I want you to take a look at this graph that explains the concept of model reference control. There is a reference model. This reference model presents the truth. It can present the desired closed-loop performance of the system. It can present the desired dynamics of the system. It is fixed. It is used as a reference. And then we have the adjustable system. Adjustable system has the ability to change its parameters. So parameters of the adjustable system could be changed. Now, our goal is to make sure that the response of the adjustable system and the response of the reference model will be very close. So what we do in model reference system, we find the error, the discrepancy between responses of reference model and adjustable system, and then we build a special adaptation mechanism. Adaptation mechanism is quite complex. The purpose of adaptation mechanism is to provide special effect on the adjustable system, such effect that would result in the reduction of this error. And I guess adjustable system could be affected by environmental disturbances, but it's a little bit different story. I want to show you self-tuning control principle, which is different from model reference. In self-tuning control, I want you to find the real physical process with poorly known parameters, the control plant. I also want you to see that the input of the physical process and the response of the physical process are being monitored. And on the basis of this data, we perform parameters estimation of this physical process. What do we do with these parameters? These parameters are used to design the controller or redesign the controller. And then when controller is redesigned, parameters of the controller are supplied to the controller of the system, and we have regular control loop that operates. The point is this: parameter estimation procedure may work on the continuous basis. Parameters of the system may change, and therefore we have to be engaged in ongoing redesign of the controller process, and adjustable controller will have tunable parameters. Gain scheduling is different. In the gain scheduling, we do not have reference model. We do not perform self-tuning. We monitor environmental disturbances. We monitor conditions that require us to change parameters of the control law. We have to perform sufficient preliminary study, and for every specific combination of the environmental parameters, we have to come up with the set of parameters of the controller. So there is controller, there is control plant, there is control loop, and the gain scheduling is a special procedure that, based on the environmental conditions, defines parameters of the controller, and it's an ongoing process. A good example is this: flight conditions are being monitored, like payload, like altitude, speed, angle of attack, and there are controllers responsible for the operation of the airframe, and these controllers are defined for every specific combination of flight conditions, set of controllers. Specific combination of flight conditions, set of controllers. Now, this problem sounds like a very complex problem. It is complex only at the design stage, but eventually we have two arrays, data arrays, array with flight conditions. We have monitor flight conditions. As soon as we match flight conditions to a particular entry in the array of flight conditions, we automatically extract set of parameters of the controller. There are people who do not believe that this is model reference or adaptive self-tuning control, and later we will talk why. And at this point, I want to start the discussion of the model reference adaptive control. And I will start from a rhetorical question: how to specify a desired system performance? What do you know about performance specification for a system? It could be time domain specification, settling time, overshoot, steady state error. It could be frequency domain specification. For example, we want particular bandwidth, we want particular disturbance rejection, we want a acceptable difference between the desired and actual closed loop characteristic, frequency characteristic of the control system. The desired performance could be defined in the S domain by definition of dominant poles and eigenvalues of the fundamental matrix of the closed loop system. You know how to do it. And it could be done, of course, in the Z domain, if we would decide to use Z domain design approach. There is another technique. It is a performance index, it is called. Performance index has normally three components. The first component describes the losses associated with maintaining particular path in the state space of the system. And the P is the matrix that defines the penalty for specific trajectories within the state space. The second term does not have integration, but this term is responsible for the final state of the system at the end of the settling time, because this term effectively represents the steady state error. And then there is another term, and this another term defines the penalty for the use of control effort. You understand that control effort is fuel. Control effort could be some valuable commodity that costs money. And therefore, this term is represents the cost of control efforts. And of course, we want to minimize the sum. How this approach is used? If matrix P is properly defined and well balanced with respect to matrix Q, and matrix Q, the cost of control effort is properly defined, then system designers may produce several versions of the system controller. And for each of these versions, the performance index could be defined, and this enables us to choose the optimal system design. In optimal control, you can work utilize so-called the maximum principle and dynamic programming. And maximum principle and dynamic programming are mathematical techniques that allow you to rigorously minimize performance index. In adaptive control, this topic is presented. But then there is another way to specify system performance by a special model that has required system behavior. It's supposed to be a simulator that has the required system dynamics. And then, if you would apply the same input at the real system and at the reference model, you can compare the response of the system with the response of the model, and this comparison provides a very good measure for finding a better design of the controller, better design of the system, or improving the design that we already have. The concept of model control is this, and I will be repeating myself. The response of a control system to the input signal must be consistent or close to the response to the same input signal of a model. Model often is a simulator, but not necessarily is a simulator. This model represents the desired properties of the system. So you have a simulator, for example, that represents the desired closed-loop system performance, and we have the real system. And we have to find a way how to force the real system to have response very close to the response of the reference model. How can we achieve the good compliance of the responses of the properties of the adjustable system with the properties of the reference model? There are two ways of doing it. First way is to perform continuous adjustment of parameters of the adjustable system, parameters of the controller, for example. And we call it parametric adaptation. The second technique is to generate an additional control effort that would force the adjustable system to follow the reference model. And this is called, unsurprisingly, signal adaptation. And eventually you will be very familiar and very comfortable with both concepts. I want you to take a look at the diagram that represents the parametric adaptation. There is a process, there is a system controller, This arrow reminds you that controller could be adjusted. There is a reference model that represents the desired closed-loop performance. Reference model could be built directly based on the design specs. So, output of the system is compared against the output of the reference model. Output of the system is always with minus. Output of the or response of the reference model is always with plus. We compute the error, and then we have the adaptation mechanism. And the purpose of this adaptation mechanism is to compute increments to individual parameters of the control law. And these increments, believe me, will be properly calculated if we would use the appropriate techniques. Meaning that we would eliminate with time this error. Model reference system signal adaptation. What you can see here is the reference model. It represents the desired closed-loop system performance. There is a control process. There is a controller. The controller has been designed based on the best guess of the characteristics of the process. However, if we would drive our system and the reference model with the same signal, their responses will be different. We extract the error and we design a special adaptation mechanism that would generate a special control signal. This control signal will be applied to the process in addition to control effort from the controller. And if properly designed, it will force the control system to have the same properties as the reference model. There are several problems that we have to address, or several problems that we can address using the model reference approach. And they not necessarily should be control problems. One of the problems is parameter estimation or system identification. We have a particular physical process, and we are not aware, we don't have good knowledge of the characteristics of this process. And in some cases, it is quite difficult to get information on the state of this process. Look, we're using information on the state of the process. However, we may need this information on a second-by-second basis. And this information could become available, let's say, every 5 minutes. So one way or another, we apply signal U to this real physical process. We monitor response of this physical process. We apply exactly the same signal to the simulator with adjustable parameters. We monitor response of the simulator. Response of the simulator is expected to be different from the response of the real process. We have error, we have adaptation mechanism, and we use this adaptation mechanism to tune parameters of this simulator. I have to tell you, in this case, the reference model that carries the required performance is the real physical process. And the adjustable system here, the simulator, works as the adjustable system. Let's see how we can perform state estimation using the model reference approach. This is a physical process with poorly known parameters and poorly known states. Our prime goal is to determine the state vector for this process. We have a simulator with adjustable parameters. And for the simulator, we can monitor state of the simulator continuously if necessary. Now, we compare response of the physical process with the response of the simulator. We extract error, and then we have the adaptation mechanism. And this adaptation mechanism will convert error and some additional information into parameter change for this simulator. In this case, we would say that real physical process is the reference model, and the simulator is the adjustable system. And if we change parameters of the simulator, we have to claim that this is parametric adaptation. If we would properly design the adaptation mechanism, this error will be eliminated, and the state of the simulator would be properly would properly represent the state of the real process. Now, there is another alternative. The adaptation mechanism could be designed differently in such a way that it would generate an additional signal applied to the input of the simulator. Still, if the adaptation mechanism is properly designed, this signal adaptation will result in the error being very low, which means that this adjustable system will generate for us, will provide the necessary system state. This is a control system. This is a control system. In the control system, we have the following alternatives. First of all, take a look at this process. This process obviously is a real physical process. It looks like state vector of this process is not known to us, or we cannot monitor it with the necessary frequency. And this is the simulator that has very similar configuration with respect to the process. However, matrix A and matrix B of the simulator are adjustable. Now, we compare state of the process with the state of the simulator, or output of the process in this case with the output of the simulator. We have adaptation mechanism. We extract the error. Error is applied, provide information to adaptation mechanism, and adaptation mechanism does the following. It can alter, adjust parameters of the matrix B, parameters of the matrix A, and if necessary, it may also inject additional control signal in the system. Apply special signal to the input of the simulator. As a result, we can get the state of the adjustable system of the simulator. The state will be available to us on a continuous basis, and this is how the state estimator will work. And obviously you have to realize that the state estimator would be used in a control system, because if you have a system with a state variable controller and we have no way of monitoring state variables with the necessary frequency, having a state observer or state estimator is a necessary condition. Now I want to talk about model reference for control systems. First of all, I want you to see a real physical controlled process. And I want you to see the controller. And you can see the control loop. The state of the controller is picked up by the controller, and you have the feedback and negative feedback, and this is a control loop. Now, this control loop probably was designed at some point, but this control loop does not work properly because at the stage of design, properties of this physical control plane were not accurately known. But then we have a software simulator, and the simulator represents the desired closed-loop system performance. What do we do next? We find the discrepancy between the state of the simulator and the state of the control system. We extract the error, and then we have adaptation mechanism. Adaptation mechanism use more information than just error, but this adaptation mechanism can generate a adaptation signal for signal adaptation. This adaptation signal would be forcing system to follow the reference, the model reference. Or you may have the parametric adaptation. Parametric adaptation will affect parameters of the controller, forcing the system to behave exactly as the reference model. So don't be confused. In this case, reference model is a software simulator representing the desired closed-loop system performance. And the adjustable system is the entire physical control system with the physical process and the controller. I will reiterate my example. What you can see here is a control system defined in terms of state variables, and the system is a model reference system with parametric adaptation. Where is the reference model? This is the reference model. It represents the desired closed-loop system behavior. It's a simulator in the flight control computer, for example. This is the real control plane, physical control plane, the feedback, state variable feedback controller, filter in the reference channel. As you know how we have to use these filters. And then what? When this controller and this filter were designed, we did not have good information about the properties of the control plane. And as a result, our system does not work that well. And therefore, if we would apply the same input signal to the reference model, to the simulator, and to the real physical system, the states will be different. And we extract the error, and we introduce the adaptation mechanism. And this adaptation mechanism is responsible for modifying the feedback controller and for modifying the filter in the reference channel. Surely parametric adaptation. This is the system, control system with signal adaptation, state variable definition. Again, this is the reference model. It's a simulator that represents the desired closed-loop system operation. This is the real physical system with the controller, with the control plane, and two components of the controller, state variable feedback controller and the filter in the reference channel. when this controller and this filter were designed, we did not have the complete information on the control plane. So there would be discrepancy between the response of the design system and the response of the reference model that is fully consistent with the design specifications. We extract the error, we have the adaptation mechanism, and this adaptation mechanism generates a special control signal. And the purpose of the signal is to force a real physical system to follow the reference model. And then you have to recall that in some cases, a reference model was a simulation code, a simulator in the, let's say, flight control computer of the system. And in some cases, reference model was a real process. The adjustable system, in some cases, was a real physical process with its controller, with adjustable parameters, or it was a simulation code. So it all depends on the specific problem. If you have a control problem, then simulation code is the reference model. It represents the desired closed-loop system performance. Adjustable system is a real physical process with its controller, but controller has to have adjustable parameters. In the case of identification or state estimation, real process is the reference model. It's a real physical process with a known state vector, perhaps unknown parameters. And adjustable system is the simulation code with parameters or with ability to apply additional signal for signal adaptation. And the same is for identification. The real process is the real physical system that has to be described mathematically, and simulation code with adjustable parameters is the adjustable system. What is the nature of the model reference approach? The nature is this. We detect the error. We call it output generalized error. We can call it state generalized error, depending on what we compare. It's a discrepancy between the output of the reference model and output of the adjustable system, or state of the reference model and state of the adjustable system. And then we generate so-called control effort. Control effort is the effort that is aimed at the elimination of this error. It could be parametric control effort, adjustment of parameters of the adjustable system, or it could be signal, special signal. Signal in the case of signal adaptation. And then we have to remind you that we're dealing with very explicit negative feedback in model reference approach. In the model reference approach, the feedback, negative feedback, is the key to the success of this approach. If you remember from the 361 class, negative feedback is necessary for successful operation of our systems, because negative feedback provides a general purpose error elimination approach. The cause of the error is irrelevant. The important thing is that error is extracted and eliminated. It should be recalled that feedback always reduces system sensitivity to variations of system parameters. It gives system some robustness. If you would check effect of temperature, for example, on a thermal process, effect of the outdoor temperature would be quite noticeable. As soon as we introduce negative feedback, we will have quite low and maybe even zero steady state error. which effectively means that feedback would surely reduce sensitivity of the system to external effects. And of course, feedback would reduce system sensitivity to system properties. Look, we may have a control plant where parameters vary with time. As parameters vary, the system performance may be degraded. However, if we would introduce the model reference approach, we will have ongoing adaptation in the system, change of parameters of the controller, or injection of a special control effort that would not allow system performance to degrade. And of course, there are disadvantages of feedback. System with feedback could be unstable, and when you will be working on the model reference systems, the instability will be a major concern. And then there is another inherent problem with the feedback. Feedback implies that the error first must be detected. It must happen. It must be detected, and then it will be eliminated. So the response of the system with a negative feedback is a little bit slow, or could be too slow for some applications. And then we have to keep in mind separation in the time domain. In any adaptive control system, especially model reference control system, one can detect two control loops. One control loop is the control loop of the control plant, of the feedback controller, which is supposed to work fast. And then there is another loop. It is the model reference approach is implemented by this loop. It's a loop that includes adaptation mechanism. The purpose of this loop is to control the controller. This loop operates slow. And finally, I want you to pay attention at this homework assignment number 1 that will be formally assigned second day of classes on the week, and it will be collected second day of classes on the next week. And I would really recommend that you do homework assignments, because if you do not do homework assignments, you would most likely fail test number 1 that will be given in class. The purpose of the homework assignment effectively is to get you prepared for the test. I understand that I do not change homework assignments for a long time. Several groups of students, several generations of students do the same homework assignment. So if you are a lazy individual, you can get this homework assignment from someone who completed my adaptive control 2 or 4 years ago, and you will get good grades for the homework assignment. But you will not be prepared for the test. This is the problem. So homework assignment is not exercise in good writing. It is exercise targeting the test that you will have.